So again, welcome everyone. Welcome to the performance price of virtual functions. This is the talk for today, and I'm going to give you some heads up about virtual functions and how much do they cost in the means of how much time do they consume, and what are the ways you can decrease their performance impact. So a short note about me. I'm Ivica Bogosavljevic. I'm in Serbia, and I'm an application performance specialist. So what does that mean? What I do is that I don't do like regular C++ development, but when people have problems with their software performance, it's running too slow, and they want to speed it up, they talk to me, and I help them debug those stuff. And I also help. I also help with trainings for those teams who have like performance critical software. I also write for software performance blog. It's called Johnny Software Lab. So just a second. So Johnny Software Lab, and this is the address of the site. So if you are generally interested in topic performance, you can use RSS feed on the site or follow me on Twitter, and you can to get notified when new stuff appears on the blog. And also you can write me email anytime you like about any topic you like related to performance, because I gladly answer those mails. So that's about me. So let's talk about virtual functions today. Now, why I wrote this presentation is that I had a feeling that there is a lot of talk about performance of virtual functions in C++, but somehow all of those they don't look relevant enough. The testing codes they use to measure performance impact of virtual functions are not what's typically used in production, and you will see later that performance of virtual functions can depend a lot on the circumstances where virtual functions are used. So I wanted to give you this talk is in this talk I'm going to give you several ways to investigate performance of virtual functions and what are the factors that influence virtual functions performance. So what are virtual functions? And we all know what virtual functions are, but they come with a performance cost. We know that as well. But as we will see in this talk, the price of performance cost of virtual functions actually depends on several factors, and it's not really easy to pinpoint. So in your environment, it can be smaller or larger, and that really depends. So let's start. So first, before digging into the topic, let's see how virtual functions work. That is, how compilers implement virtual functions, because this is where the performance cost comes from. So C++ standard doesn't mandate how virtual functions are implemented. They can be implemented in any ways, but however, most compilers implement them in the similar manner. So what's the deal with virtual functions? So the address of the function is not known at compile time. So at the compile time, address of function is not known. Each object that we are currently processing in some critical loop can have a different function, and this address of the function needs to be looked up at runtime. Now, for each type in your program, there is a virtual function table. So each type. So if you have 3 classes, 2 classes base and derived, there is one virtual function table for the base class and one virtual function table for the derived class. And each instance, so each object, not each type. Now each object has a type. Each instance of the type has a pointer to this shared table. So all the instances of the type base shared one virtual table, but each object has a pointer to this table. Now, what does the compiler know? Compiler knows the offset. So the addresses of the functions are kept in this virtual function table. And the compiler at compile time, it knows the offset in the table. So it doesn't know the offset, but it doesn't know the address. So what happens when the call to the virtual function is made? So what does happen? The compiler knows the offset. So the program follows you're processing your instance. Runtime accesses the pointer, follows it to the virtual table, And in the virtual table, it knows the offset. It goes to the offset in the virtual table. So line entry in the virtual table, and then it reads the function address. And then knowing the function address, it then calls the function. So here is an example. We have an array of instrument pointers, and there are instrument class. And each of these, there are several classes derived from instrument class. There is a wind, like a wind instrument, percussion, string, and brass. Now, each of these instances has a pointer to the virtual function table. So this is the table for the wind class. This is the address of the play. This is the address of the what, and this is the address of the adjust function. And for example, in the brass object, you see that the play and what belong to the brass class, but adjust belongs to the wind class. So because this is derived from the wind class, the brass object, the brass class doesn't implement adjust function. It just uses inherit one from the wind object. When we are dealing with non-virtual functions, the function address is known at the compile time. So it's really simple to call. So the compiler just needs to emit a jump instruction or call instruction to the address. Now, when it comes to virtual function, as you have seen, it's more involved. So it's more expensive, and that's clear. Just the implementation is more complicated. So here is how it looks. We have a pointer to the instrument element, and then we go to the object, which is actually brass object, but we don't know this yet. We go to the virtual point. We follow the virtual pointer to the virtual table of the brass class, and then we go to the offset number 2, which is wind adjust. So we'll take the address of this function, and then the CPU goes to that, calls that function. So let's first establish what is the performance price of virtual functions. We have a vector of 20 million objects of the same type. So they're all the same type. There are no derived, there is no derived, there is no base classes. And then we have 20 million calls to the virtual function versus 20 million calls to the non-virtual function. So this is a virtual function. It uses the virtual dispatching mechanism. And this is a non-virtual function. It is also virtual, but it is also called. The function is not in line, or there is no other optimization done. So if we have a short and fast function, the virtual function's call is slower, but not much. 153 milliseconds compared to the 126 milliseconds for 20 million objects of the same type in a vector. If we have a long and slow function, then this difference is almost negligible. So for a really short and fast function, there is some overhead, maybe 20% in my measurements, but for long and slow function, it's almost invisible. So the first, what we can say is that the results don't look that bad. There is some overhead for small function. For large function, there is almost no overhead. But the question is this all there is to virtual function? And the answer is no. No. Okay, so what's next? What's important about to understand virtual function performance? So the title of this slide is Vector of Pointers. So how is virtual dispatching mechanism activated? It is activated when we are accessing our object either through reference or through a pointer. So what does that mean? Is that the object we are allocating needs to be allocated on the heap. The objects we are accessing, calling virtual method, needs to be allocated on the heap. And what's the problem with that? Well, if your object is allocated on the heap, access to it can be very slow due to data cache misses. So what does that exactly mean? So imagine you have a vector of pointers. Now imagine, so these pointers are neighbors in memory because they're in a vector. But the things they point to are not necessarily neighbors in memory. They can be scattered around memory in any way. So if you have neighboring pointers in a vector, but they don't point to the neighboring elements of them in the memory, the performance of such code can be really poor. And the bad thing about this is that normally pointers are pointers are, sorry, not pointers, memory for these objects on the heap is allocated using new and released using free, which internally use malloc and free from C. And there is absolutely no guarantee that the neighboring pointers will point to the neighboring elements in the heap. In fact, as your program becomes bigger and more complex, there is less and less chance that this will happen. So if your program is small, for small program, you can say that you can expect not that much of a performance difference if you're using virtual vector of pointers or vector of objects. But if you're using a large program and there's a lot of things going on for the system allocated, then the performance can get bad. So vector of pointers is one alternative. The second alternative is a vector of object. Vector of objects is much better for the performance compared to vector of pointers. And why? Vector of objects don't suffer from data cache misses. So if you have 20 million objects in a vector, that is just one single allocation from the allocator. But if you have 20 million object pointers in a vector, that's one big vector that holds the pointer and 20 million allocations on the heap for all the objects that these pointers point to. Now, as I already said, is that the performance actually depends if neighboring pointers point to the neighboring addresses. So we have here optimal layout or perfect layout. So we have here that element number 0 points to this class, element number 1 points to this class, but these are all neighbors in memory. So this is all neighbors in memory. This is an optimal layout. This is like a perfect layout. And if you have a layout like this, you won't see a lot of performance. You won't see a performance degradation. But here is a non-optimal layout. So we have neighboring elements in neighboring pointers, but they don't point to the neighboring blocks in memory. See, this one points to this one. Point number 1 points to this one. As this is a non-optimal layout. No, so normally your program during its runtime will be something in between. It won't be completely optimal, but it won't be also completely non-optimal. I mean, to have non-optimal layout, you have to really push it hard. So let's do an experiment. At the beginning, we have a vector of objects containing 20 million objects. Okay, so we have a vector of objects with 20 million objects. We have another vector of pointers, and pointer at location E points to an object at location E. So these vector of pointers just point to the vector of objects we just allocated. And we have, if we set it up like this, that the pointer at location E points to an object at location E, we have a perfect ordering because neighboring pointers point to the neighboring objects. Now what we do next? We measure the time needed to iterate through 20 million objects by following the pointers in the vector of pointers. So we are iterating through the vector of pointers and we are following pointers. So this is what we initially do. But in the next iteration, we pick a random pointer in the vector and swap it with the pointer at place 0. So we are actually shuffling the pointer vector. We are making it, as we do this, every time we do this operation, every time we swap pointers in the pointer vector, we slow it down a bit, okay? So how do our performance number look like now? Well, here it is. So we have, remember, we have a vector of 20 million elements. So at the beginning, so there are two functions we measure. We measure runtime for a virtual function and runtime for a non-virtual function. As far as runtime, you see that most of the time they're almost the same. So there are some difference, but it's not the difference in speed here doesn't come from using the virtual dispatching mechanism. It comes from data cache misses, and it comes because pointers in the neighboring pointers do not point to the neighboring elements in memory. So if we do relatively little pointer swapping, so the runtime is about 200 milliseconds, and it's stays like that until we do 64K swappings. Remember, we had 20 million elements. But as we're swapping more and more and more and more, after we've swapped most of the vector, the runtime just goes from 200 milliseconds to 1.5 seconds. So it's about 7 times slower. So As you can see in this graph, the memory layout is tremendously important for program performance. So the reason is because the modern CPUs are much faster than the memories, they have to wait for the data. If the memory layout is not good, it's not in a vector, then this can slow down considerably your program. So worst case is 7.5 times slower than the fastest case. Now, this slowdown is not related to virtual functions. As you've seen, there is the same slowdown that comes with non-virtual functions. It is related to memory layout. But the question is, why do you want to use? Why would you want to use a vector of pointers? And you want to use vector of pointers to achieve polymorphism. So this is the main reason. And if you want to use polymorphism, that means if you want to have polymorphism, that means you will have to use vector of pointers, and worst case can be really bad. So are there any alternatives to vector of pointers if you want to have similar behavior? So use STD variant with STD visitor. So there is this STD variant, I think it's introduced in C++ 17 or maybe 14, that you can use. So instead of having pointers, it keeps all the elements in the vector itself. It doesn't allocate externally memory. I also wrote one container called polymorphic vector, which uses virtual dispatching, but it doesn't use pointer. The downside is that it has an increased memory consumption. There is also another approach, is that if you have like collection of objects and you do type-based processing, you first process all the objects of type A, then all the objects of type B, and then all the objects of type C, and keep each of them in an individual vector. So this has several benefits. But one of them is that you're avoiding these allocations on the heap, and you're avoiding fouling pointers, and generally this gives good performance numbers. But this works only if you don't need a specific ordering in the vector. So if you need a specific ordering in the vector, then it doesn't work. There is a container in Boost called base collection that you can use to have this. Okay, this finishes the topic of vector of pointers. So next question is, why are virtual functions slow? And the answer is compiler optimizations. So what's the deal with that? So compiler knows the address of non-virtual functions at compile time. Compilers do know those addresses, and then this means that the compiler can inline the non-virtual function and completely avoid the function call. Now what happens then? Inlining saves a few instructions on the function call, but that is not the whole point of inlining. After the compiler has inlined your function, the compiler can perform many other compiler optimization. For example, it can move. Here there are two. I gave here example of two optimization. It can move loop invariant code outside of the calling loop. So loop invariant code is if in the loop there is some, for example, condition, if, or calculation that is all same in all the iterations of the loop, then the compiler can move it outside. What also compiler can do is can use special instructions that can process more than one data at a time in a process called vectorization. So these vector instructions, there are special instructions in the CPU, and the compiler can actually use them only if it inlines the function body. So if it can copy the function body into the loop that is calling the function. So we did here one experiment to see what's going on with compiler optimization, with inlining and so on. So how does it look like? We have a class object which has this members. It has is visible, has an ID, and this has this static member called offset. Now we have two methods. One is visible, and the second one is called getID3. I don't know why ID3, but getID3, which returns MID plus moffset. So this is the class, and this is our testing loop. So we go through array. I think it's 20 million elements again. We take an element out of an array. So we take it with this call, and then we check if it's visible. And if it's visible, we update the count by calling getID3. And notice here that getID3 returns MID plus moffset. And the M offset is a static member which doesn't change. It's same for it is same for all the instances of the class. Okay, so we measure the performance of non-virtual functions. So we don't measure virtual functions. We are measuring non-virtual functions when they're inlined and when they're not inlined. So if we have a vector of 30 million objects, the inline will take 136 milliseconds, and the non-line will take almost 2 times the size, 242 milliseconds. So why does this happen? So it happens because when the compiler inlines this get ID3, this loading M offset from the memory is the same for all in the whole loop, in the whole for loop. It's same. This member never changes. When it lines it, it becomes aware that this loop, this value is loop. How to say? It's loop invariant. It doesn't change its value, so it can optimize away loading of this value from each iteration of the loop. It moves it outside of the loop. It loads it once and then it stays there. And this is why we see this performance impact. Some of the performance speedup you get it because you get rid of the function calls, but other you get them because you are not using it, because the compiler actually got rid of some of the useless work. So what is the conclusion behind this? Well, virtual functions cannot be inlined because their address is not known at compile time. And because of that, they're essentially not inlineable. So what can we do about that? So if we want compiler optimization, we just need to wait somehow to get rid of virtual function. And one of the solutions for this is already talked about. It's type-based processing. So you have each vector, each type of object is held in a separate data structure, in a separate vector. So don't mix the types. Each type has its own loop and its own processing. Now, when you do it like this, the compiler can inline small functions and it can perform compiler optimization. You have that already implemented in Boost-based collection. But of course, this works only if the objects in the vector are not sorted, don't have to be sorted. Now you might ask yourself, is it worth it? Is it worth it to do something like this? The problem with this is that the benefit of compiler optimization that happen because of inlining are really case dependent. Some code can profit a lot from compiler optimizations, other almost not at all. In principle, smaller functions benefit more, but not necessarily. So it's all case dependent. So next topic is I call it jump destination guessing. So let me tell you what it is. So to speed up computation, modern hardware does a lot of guessing. So the technical term for this is speculative execution. So in the case of virtual functions, the CPU tries to guess which virtual function will get called. And then it starts to execute instructions that belong to the guessed virtual function. So if there is a certain pattern, if you're processing object in a loop and there is a certain pattern to how the types change, for example, if your vector is sorted by type, then this guessing mechanism works correctly. If the guess is correct, so if the address of the function is guessed correctly, this saves time because the CPU has already done some of its calculation. But if the guess is wrong, so the CPU needs to cancel the effect of wrongly executed instructions and start over. So guessing wrong costs time. If you guess the wrong virtual function, it will cost you time. So let's do an experiment. We have 3 vectors of 20 million objects. So first vector is sorted by type. So at the beginning we have all the objects of type A, then all the objects of type B, then all the objects of type C, and then all the objects of type D. In the vector number 2, types are sorted. They're not sorted according to type, but they're sorted. The types are changing in a predictable fashion. So you see here, A, B, C, D, A, B, C, D, A, B, C, D, A, B, C, D. In the third scenario, types in the vector are completely random. So the vector element number 0 is B, element number 1 is C, A, C, A, C, B, B, A, C, B, A, and so on. What we do is now we measure the time needed to call small virtual functions on these three types of vectors. So we're calling the small virtual functions three types of vectors. So we don't have the problem that we are accessing through pointers. We have a perfect memory layout, so there are no data cache misses. So performance of virtual functions depending on the sorting type. If they're sorted by type, it's slightly less than 200 milliseconds. If they're sorted in a round-robin fashion, it's again slightly less than 200 milliseconds. But if they're unsorted, it's 500 milliseconds. So what happens in the first two scenarios? The guessing hardware, which guesses the function address, works fine. It guesses the function address correctly, and this saves times. But in this case, it doesn't work correctly. So it will try to guess, then it has to revert the work it was doing. The CPU has to revert the work it was doing and start over. And you see this clearly in this graph. So what is the conclusion? If there is a pattern in the vector, if the types in the vectors are sorted in a predictable manner, the CPU can predict the address of the virtual function it needs to call, and this typically will speed up computations. This will be visible for small virtual functions. If types are unsorted, the CPU cannot guess successfully and precious cycles are lost. And again, the solution is type-based processing. However, as already said, type-based processing is not always usable. So this effect is mostly visible with short virtual functions. Okay, this is the last topic. It's called instruction cache evictions. So I assume you don't know what instruction cache is and what instruction cache evictions is, so let me elaborate here. So modern CPUs rely on getting to know. So this is with apostrophes, getting to know the instruction they're executing. So what does that mean? If the CPU has recently executed some code, it is hot code. So what does that mean, that some code is hot? So if the code is hot, that means its instructions are in the instruction cache. Instruction cache is very similar to data cache. It is used to speed up access to instructions. So its branch predictors know the outcome of the branch. So there are branch prediction, there's jump. So we talked about jump destination guessing. There is also branch outcome guessing. It works really similarly. It tries to guess if the branch will be taken or not. If the code is hot, it will the CPU will know the outcomes of the branches, and it can more successfully guess if it is going to be true or false. The jump predictors know the target of the jump. So the hot code the CPU has executed recently, it knows some statistics about it, and it can use those statistics to speed up execution of that code. So CPU is faster when it is executing hot code compared to executing cold code. And now the CPU's memory is limited. The size of instruction caches, of branch prediction caches, of jump prediction caches, they're limited. So only some code is hot. All the other code is cold. The code that is currently hot will eventually become cold unless it is executed frequently. So if it executes frequently, it will be kept hot, but once it is not executed anymore, it will become cold, and eventually it will be evicted from the instruction cache, from the branch predictor cache, from the jump predictor cache. Now, what does it have to do with virtual functions? Well, virtual function, and especially large virtual function. So we have a virtual function, but large virtual function, and each object has different implementations. So object has one implementation of the same virtual functions. Object 2 has another implementation. This means that we are switching from one so when the CPU is iterating over these vector of these objects with large virtual functions, that means the CPU is always switching between one implementation and another implementation and a third implementation. And what does that mean is that since it is never executing the same code, it is always executing cold code. It is never executing hot code because it is constantly switching between different implementations.
I got a question.
Yes.
How long can we expect code from remaining hot on modern CPU?
Oof, that's really, I mean, that's really case specific, and it's really, you cannot tell it. There is no like, way to measure it. That's also the problem. But for example, if you have a virtual function just returns one value, or maybe a virtual function like 10 or 20 instructions are typically not the problem. But if you have a virtual function which is really large, completely different implementations for different objects, that this will be measurable. This will be visible. Okay. Now, to measure the effect of instruction cache eviction, this is the hardest because it depends on many factors. So it depends on the number of different virtual function implementations. So if you have 100 objects and each one of them has a different virtual function, then you will get always cold code. Now, there is also one important metric is the number of executed instructions in the virtual functions. Now, we have a virtual function that can be large, but actually, if you look at the executed instructions, only like a small part of the function is executed. So this is not a problem. But if you have a virtual function where all the function is executed, where all the instructions in the virtual function is executed, then the larger is the number of instructions, the slower is the code. The size of virtual functions correlates to the number of executed instructions. I mean, bigger instruction typically means more instruction executed, but they're not the same. So what is also important is how sorted are the objects in the container by type. So best case is when they're sorted by type like this: AAA, BBB, CCC, DDD. So first objects of type A, objects of type B, objects of type C, and so on. The worst case is where they are sorted by type in a round-robin fashion. So you have, this is the worst case: A, B, C, D, A, B, C, D, A, B, C, D. Because A is hot, now B is forgotten. Let's say you're here. You're executing A. You have executed D recently, but you will not execute D until 2 more iterations. And in the meantime, because you will be executing B and C, you will forget D completely. Okay, so let's measure the effect of this. So we have 4 classes: rectangle, circle, line, and a monster. And we have 4 implementation of long virtual function. There is a long virtual function for each of them. So the long virtual function consists of a for loop with a large if, else inside it. So this is a large for loop, and there is if, else, so on. So the virtual function is actually quite large. To measure this effect, we use 2 vectors. The first is with 20 million objects. When the elements are sorted by type, so this is like the best case. And the worst case when the elements of the vector sorted by type in a round-robin fashion. So A, B, C, D, A, B, C, D, A, B, C, D. So we wanted to measure it, change the size of virtual function. So we want to be smaller, and then we increase the size of the virtual function and see how the runtime changes. So how we change the size of the virtual functions? Well, there is if else block, and we add or remove some of the conditions inside the block. And we need to compare the time needed to iterate 2 vectors. So how does that look like? So this is the relative performance difference between the sorted and round-robin vector. So this is a sorted. Relative means that we divide the runtime of the round-robin, we divide it by the runtime of the sorted. So when the virtual function is small, it is almost 1. So there is no performance difference. But as we add more, so this number is 20, 40, 60, 80 is the number of if-else blocks. So if number of conditions in the if-else if block, we go 20, 40, 60, 80, 100. So as you see here that the performance is degrading, and it is worse when we are having like a 40 of 40 elements, and then it stays most of the time around that. So the starting from 1, it goes down to 0.6, and then it's between 0.6 and 0.7. In the worst case, the same function took 7.5 seconds to execute in the sorted vector and 12.3 seconds to execute in the round robin vector. Okay, so you see the effect. So it will be about 1.6, 1.7 up to 2 times slower if the objects in the vector are not sorted. And of course, the bigger the virtual functions, there will be more, the effect of instruction cache eviction will be more pronounced. Of course, the same problem will happen if you have smaller virtual functions but larger number of objects, of types. So you have 100 types but smaller virtual functions, you will see the same effect. So this phenomenon is not related to the virtual function themselves. So if you have like a class, objects of the class, even they're same type, and then each object has a pointer to a function, just a classical C pointer, and each instance has a pointer to different functions, you will see the same effect. But what you will typically see, this effect occur with large virtual functions on a mixed type unsorted vectors with many derived types. So you have large virtual functions, mixed type unsorted vectors, and many derived types. And then you will see this effect actually. This is the end of the talk. So what is the conclusion behind everything I talked about is virtual functions do not incur too much additional cost by themselves. The cost of virtual function doesn't happen because there are more instructions executed. It is the environment where they are executed which determines their speed. What the CPU, the hardware, craves is predictability. It wants same type, same function, neighboring memory addresses. If this is true, the hardware will run at its fastest. But it is really difficult to achieve if just you're casually using virtual functions. So if you're just using them without giving it a lot of thought, you will not get this behavior. In game development, where speed is important, they want to use the hardware the best way possible because it will make the game run more smoothly. They use another paradigm instead of object-oriented programming. It's called data-oriented design, or sometimes it's called entity component system. Now, one of its major parts is type-based processing. So each vector holds one type only. This eliminates all the problems related to the virtual functions. I mean, you can have virtual functions in the code, but because you're using type-based processing, this mechanism is never executed, never used. This is a good approach if you want speed, but it is not applicable everywhere in the general software development. But in the game development, it's fine, and they use it. And actually, their code bases look different compared to OOP code bases. It's really interesting to have a look how that code is written. There are some really nice ideas that you can take from that, even if you don't use the paradigms they are using. So what are the lessons learned? So if you need to use virtual functions, you need to bear in mind a few things. The number one factor that is responsible for bad performance are data cache misses. And you'll see that everywhere, not in virtual functions. Data cache misses is actually what's making your programs run slow. Avoiding vector pointers on a hot path is a must. So you cannot get good performance if you have vector pointers. Other factors also play their role, but to a lesser extent. So as we've seen in the lecture, data cache misses are the vector of pointers. So in that case, the code was like 7 times slower. In all the other cases was like 2 times slower, 1.5, but 7 times is something that you should really try not to have. With careful design, you can reap most benefits of virtual functions without incurring too much additional cost. So here are a few ideas to fix your code with virtual functions. First, arrangement of objects in memory is very important. That's one thing. So try to avoid vector of pointers if you're into speed. Use vector of objects or other proposed containers that guarantee that the neighboring objects in memory guarantee that you're iterating over neighboring objects in memory. What you also want to do is to try to make small functions non-virtual. Most overhead of virtual functions comes from small functions. They cost more to call than to execute. So this is what you can also do. If it's possible, you can also keep objects in the vector sorted by type. This also helps. And that's it. Now, questions.
Okay, we have one question from André. One advantage of OOP is that you can add a new type to the application without modifying a lot of code. Does the technique of vector of objects loses that?
So the main problem with how all these, if you're using vector of pointer, I mean, if you have a class hierarchy, it's not related to the way you store it in the vector. So you can pick the way you store it. You can use vector of pointers. If you use vector objects, then all the objects in the class, in the vector must be of the same type, but that doesn't work always. What you can actually do is use STD variant. So, and then with the STD variant, you can make mixed type vectors, but they are all allocated in a single block of memory. So they're all allocated in a single block of memory. And when you're iterating it, they're all neighboring elements in the memory. So STD variant is fine. There is also, I mentioned this polymorphic array, which was like an exercise of mine. I wanted to see if it's possible to use virtual function dispatching mechanism and use one block of memory. And actually it is possible to do. And it also guarantees really good performance. The worst thing is about this is if you have 20 million objects, for example, 10 million objects, the size of this vector will be 20 million times the size of the largest class. And sometimes you have performance consideration, but you also have memory considerations. And sometimes this is not a good approach. But it all depends on your current circumstances, like everything related to performance.
Have you measured the impact of devirtualization? Is final really helping?
So I can tell you, I didn't measure, but I can give you my thoughts about it. So devirtualization would actually help, because in that case, the compiler can treat the function as a non-virtual function that is completely inlineable. But the problem with devirtualization is that devirtualization doesn't work except for trivial examples. I mean, if you have a vector of objects or you have hash maps, whatever data structure you have, and the compiler cannot devirtualize that. So the compiler can devirtualize it only in a under very limited circumstances that most people will find it not interesting. Like, this is not hot code.
Yeah, and the second part of the question is final really helping?
I mean, that really depends. If you put final and the compiler manages to devirtualize that function, it will help. If you're lucky enough that this is your hot code, that it will definitely help. But all depends on the compiler and how compiler is good at doing this performance optimization. Now, final would help if this is a hot code. If it's not a hot code, then it won't help. I mean, everything I talk about here in this presentation, if you're having you have a vector of pointers, and then you switch it to a vector of objects. But this vector of pointers takes like 2% of the runtime of your programs. Now it takes 1%. Then the overall runtime, it doesn't matter, because you are even doing performance optimization. So you're always focusing on the hot code. So not something irrelevant. Same with final.
Any tool you'd recommend to analyze cache misses, quantity, etc.?
So yes. So actually, there is a complete methodology. If you have your program, and then you want to, if you have a program and then you want to see you want to see, you can use a profiler to see which code is hot. That means which code is actually taking a lot of time to execute, but it won't tell you why. And sometimes the reason is not sometimes, oftentimes the reason is data cache misses. If you're working with classes which are like not like really small classes, but if you're having like classes which more than 4 data members and you're processing them in loops and so on, you will see data cache misses. That's almost guaranteed. Now there are tools that you can use to do this. One is called, the best one that I know, it's called, it's an Intel's tools. It works on Intel's CPU. It's called Intel vTune Profiler. And it can tell you which functions in your code have data cache misses. This is a great tool. I would really recommend. There is another tool called PMU tools. It's a runtime, but it also works on Intel's compiler. It's just open source. Unfortunately for AMD, there are ways to do data cache analysis, data cache miss analysis, but it's much more complex and it's much more involved. If you are interested in this topic, stay after this talk. I will be in the Discord, in the Coffee Machine 2. I will be there and I can answer your question. We can chat. And also on the Discord channel, there is the name of this talk. In this channel, I'll answer questions for the next half an hour after this talk.